budget and being exceptionally frugal, the magnets got wet and waterlogged and things like that. So the year before they got the machine to work, I was not a member of the Fermilab staff, but I'm told that it was the longest year in the life of that. But there was an end, and on February 12th, early in the morning, in 1972, they managed to accelerate the beam of protons up to just over 100 billion electron volts. The previous world record was held by a machine in Protvino in the Soviet Union, which was 76 billion electron volts, so there was great celebration for having seized the world record. And in a nice touch, some of our colleagues from the Soviet Union contributed a bottle of vodka extra, which was drunk in the control room on the occasion of this. Now, on that very night, at 4 in the morning, the first experimental events were recorded. And this was a very interesting collaboration. This was in 1972. Richard Nixon and Leonid Brezhnev were the leaders of the two superpowers. They were both pretty tough characters. Nevertheless, they thought that it would be nice to encourage cooperation between the two superpowers, rival superpowers, in an area which could be of no threat to anybody, namely particle physics. So that was our good fortune. And through the friendships of some of our colleagues on this side and on the other side, one of the first collaborations formed was this one from the Soviet Union, the Joint Institute for Nuclear Research in Dubna, and from a number of American institutions, including Fermilab. They had the clever idea that it was one thing to accelerate the protons to high energy. It would be another trick to actually get them out of the machine so you could do experiments. So they resorted to an old technique, which was intercepting the beam as it was circulating in the ring. And they did this with a thing that was a little motor that could turn at 3,600 revolutions per minute. On this was a polyethylene foil, specially shaped, and so it went around and around like that. It would intercept the beam, and they could detect particles that were scattered by this very thin target, so thin that it wouldn't intercept, wouldn't bother too much, wouldn't absorb too many of the beam particles. And so they took their first data that very first night that the accelerator reached 100 GeV. I've now seen a photo of the prototype of their little apparatus, and I did a little research, discovered that that prototype was made in 1970. In 1971, someone else invented the weed whacker, and if they'd been a little faster to bring their invention to market, we could have paid for the rest of the experimental program. But they were focused on physics. Later on, they added a new feature, which was to send a supersonic jet of hydrogen gas through the beam. That was even better, even more tenuous beam. And because they were inside the accelerator, they could actually make measurements as the beam energy increased during the acceleration process. So that was a very nice piece of work, and it was wonderful on the day the accelerator began to work to get some data. Within a couple of weeks, by the beginning of March, thanks to twiddling with some dials in the radio frequency building, the design energy of 200 GeV was reached, and that was cause for the celebration, not with vodka, but with some unknown liquid this time. Oh, for the days of Dixie cups. Now, the first experiment to actually publish data came from this device called a bubble chamber. So this was a 30-inch in diameter device, under pressure, superheated liquid hydrogen, so that when charged particles fly through it and relieve the pressure, a chain of bubbles forms. They look like this. This was brought to us by people from Argonne National Laboratory. And I don't know if this is an early example of product placement or what in the right corner there. So the bubble chamber pictures are iconic and wonderful because they give you, when you take stereo views, three-dimensional views of the particles. It's a little clunky in the sense that it's slow, and you see a picture is there forever, but then you digitize the picture, so it's real physics to analog to digital and back and forth. But they are beautiful and they're iconic. And we were all so taken by these when they first came because it was the first step into a new energy regime that we just wanted to collect these pictures. I remember Richard Feynman coming here and wanting to take home a sheaf full of bubble chamber pictures because it was our first look at many particles, many was 10 in those days, being produced. Here's another one of those images. So they actually produced the first publication. Here's a scanning table showing one of our scanners looking at the bubble chamber pictures. They would be projected on a very flat table, and then either using curved pieces of plastic or later on by being able to digitize them with electronic devices, one could measure the trajectories of the particles coming out. So they submitted on the 21st of July, and this was published in the Journal Physical Review Letters, the first experimental publication from Fermilab. What they did here was a stupendously simple thing. They simply counted the number of pictures they had, which there were 2 particles coming out, or 4 particles coming out, or 6 particles coming out. So easy stuff. You've got to get the efficiencies right. Nevertheless, by looking at this, and then by some more complicated things, more sophisticated things that they and their competitors at Other Energies did in the succeeding months, we were able to learn lessons about how particles are produced out of the concentration of energy that comes about in these collisions that still hold today as our paradigm for the way particles are produced. And it was all because this is such a visual and revealing medium for doing experiments. That same summer, at the end of the summer, there was an International Conference of High Energy Physics. This is our biggest meeting that happens every 2 years. It was half in Chicago. There were parallel sessions at the University of Chicago where there are lots of rooms for small meetings. And then there were the plenary sessions in this auditorium, as you've heard before, with the funeral director's chairs taking the place of the comfortable seats that you have now. Our artist, Angela Gonzalez, designed the covers for the 4 volumes of proceedings of this. The first 2 speak to Chicago. The second 2 speak to what was to become Fermi National Accelerator Laboratory. And this was, for many people, especially from our colleagues from abroad, the first acquaintance they had with the new laboratory and the way it was working and getting started, and the first acquaintance with the Fermilab look, for which Angela was largely responsible. Many posters and covers of reports. It was, she did one for me. It was a very nice piece of work, I thought, but when I had a cover from Angela on it, I thought I'd really done something. One of the high points of my young career. And the other aspect of the Fermilab look, which is a collaboration between Angela and Bob Wilson, is the bright colors, the strong forms that we have around the site. And the general look of the site, again, you can see strong colors here and there, and the high-rise building in which we find ourselves toward the background. Wilson also had a brilliant act, a brilliant stroke. There's a cooling pond that you see, a canal inside the ring. That was needed to provide fresh water that would cool the magnets, the electromagnets that were steering the beam around. And he had the brilliant notion to use the dirt that was scooped up from there and put it on top of the beam, not as radiation protection, but so that if you were flying over, you could see that human beings had done something exceptional underground there. Instead of making it invisible, he wanted to make it visible. Before he hired me, he also gave me a test. He said that he learned that I came from California, not from some junior university, by the way. And so he figured I must like to ski, and he promised me that if I would come to Fermilab, he would take the dirt from the canal and build me the highest mountain in Illinois. So I'm pretty sure this was a test to see if I could estimate how high that highest building in Illinois would be, and I didn't want my name attached to it. Anyway, he did the right thing. Now, there is the matter of the high-rise. This lovely building, now called Wilson Hall. Wilson was a teller of tales, and so I can only report to you what he told me, not whether it's true. He had an artistic bent, and he said while he was contemplating what to make for the laboratory building, he considered various things, campus-style buildings relating to each other. But he was much taken with the French cathedrals that can be a great distance. He was reading, he says, Henry Adams' book, Mont Saint-Michel and Chartres, and that inspired him to make something here that could be seen from a great distance. So what you see back there in the mists is Mont Saint-Michel from a distance. As you approach it, it looms larger and larger and larger, and that was the model. So here is our building with its great vault in the inside. There's another story also from the French cathedral that went with Wilson's story about this building, and that was that he was fascinated by the Cathedral of Saint-Pierre in Beauvais, about an hour and a half north of France. You see it on the left. You see its great vault on the right. It has a little resemblance to our high-rise building, but not that much. But what really fascinated Wilson about this was that it was completed at the end of the 13th century. The people who built it, the local bishops and his supporters, wanted it to be the highest Gothic cathedral anywhere, and for 4 years it was, until it fell down. It was rebuilt after an interval of a century or so, and then a much higher tower was added to it, and after 12 years, that collapsed. Wilson was a man who didn't like to over-design things. He liked to cut corners. Sometimes his things fell apart as well. So he was fascinated by the notion that you should do something impossible. And if it fell down, you'd learn your lesson and build it again. So that's the great cathedral at Beauvais. Now, one thing he didn't bring to Fermilab that I learned recently in a visit to Beauvais is in this cathedral is a fantastic astronomical clock installed in 1876. This is a very intricate mechanical computer that has 52 dials reporting various information, the phases of the moon, the position of the sun, the time of the day, the tides at Mont Saint-Michel, astronomical symbols and all of that, all done mechanically in the days before microprocessors. So if there happens to be an artistically inclined patron in the audience, I think we could use one of these to complete the analogy that Wilson had in mind. I want to say a few words about my colleagues in theoretical physics. Here you see my colleagues in the theory group, plus a few of the people from nearby institutions and the rest of the laboratory who regularly spend time with us. They're all brilliant, as you've already heard. But what is a particular pleasure to me, and a particular pleasure of our everyday life, is that there are at least 15 passports, 15 national origins represented in this group of people. And that partly reflects the fact that this is a great lab that attracts the best of people from all over the world. Some of them have studied in the U.S., some of them have studied abroad. The people who come from elsewhere enrich our experience. When they leave Fermilab, they are enriched by that. So that is part of my life that I value very much. What do we do? Well, what do theorists do? There's a lot of laughter, a lot of storytelling, there's a lot of coffee drinking. We make funny diagrams like this that we use to calculate things. We talk to our experimental